In 5, practice 3, microstructural change during arc welding. The objective of this practice is to evaluate the microstructural change of the plate with the welded steel through the process of welding electric arc.
For this practice, we'll be using steel plates, electrodes for welding, silicon carbide, clothes and microclothes, and phenolic resin. First, we must weld a uniform cord with 2 plates. Then we have to cut it on the cutting machine on the welding section. And then we must prepare a backlit on metallographic preparation. And then after that we can analyze on micro hardness test of beakers through different areas. Then we obtain the photomicrographs and the main zones and subzones of the welding.
After we did the chemical attack on both samples, we observed them in the microscope with different magnitudes, and we were able to observe several differences. First of all, the shape of the grain. In the welded area, the shape was thinner, like a strip, with almost no space between a grain and another, with the matrix in between. And the unwelded sample had round-like shape of grains, with a lot of space between one grain and another. After that, we used the ASTM grain size formula to calculate the grain size of each sample. In the welded sample, the grain size was 8.12 ASTM, and in the unwelded sample, we had 7.32 ASTM. In the ASTM scale, the larger the number, the smaller the grain of the size. This means that in a welded area, the grains are smaller. And if we talk about mechanical properties, this means that the welded area is going to be stronger. It will have more resistance to stress. And this will also make the material brittle. And it will lose a lot of ductility and a lot of conductivity, but it will gain a lot of strength.
We make 10 beaker tests to the weld plate and 3 to the normal steel plate. This to compare the hardness of the material.
Now in the images we can see that the test results of the 10 proofs for the material with arc weld. And here we can see that the first 4 and the 10, the hardness is around 177 to 190, and the test 5 to the 9 are in the weld zone. And in the second image we can see the proofs for the normal plate, and the biggest and the higher hardness is 170. That is lower than the lowest proof of the weld zone.
Arc welding is a welding process in which the heat required to fuse the metal is obtained from an electric arc between the base metal and an electrode of the machine. The temperature produced is about 4,000 Celsius degrees to 6,000 Celsius degrees. So for the process of welding, we have to clean our pieces so we can remove the dirt, any oil or grease present in our pieces. When the heat is obtained, it melts the metal that we are going to joint, and it produces a melted metal pool. The space between the two plates that we're going to weld is known as the arcator. In our case, we use copper wire in the electrode that was that it is used as the conductor of the energy. Although our piece was not weld, we could see in the Vickers test that our hardness increased in the welded part.
By welding steel, we found some advantages, such as saving time, saving material, just it's cheaper than the heat treatment, and it's easy to learn, and also it improves the high production and rates. Yet, it affects on when force is applied, it tends to break in that part, and also loses ductility, and it works different on high temperatures because its properties tend to change, and it also affects on the aesthetic part.
It's important for the mechanical engineers to know the arc welding because this is very used in the industries, and also we will use it in next practices in laboratory.
I think that as a mechanical engineer, we must know how to analyze the welded zones because the mechanical properties change, and this is very used in the industry, so we must know how to improve our materials.
I think this practice helped us to understand the process of welding, which is used in many industries, and it also helped us to see that the materials that we have can obtain new properties.
I think it's important to understand what happens to a material after it's welded, because welding sometimes may seem like a viable solution to fix something that broke, to join pieces together, but the mechanical properties of that specific area that is being welded change, and the functionality also changes. So if that specific area is submitted to some kind of force, it may react different to a piece that is not welded. So we need to understand what happens to the material macroscopically and microscopically.
I think that